So that was the comparison-based sorting, the order of n log n sorting, divide and conquer based sorting. However, there are special cases of order of n sorting can be possible, and let's look into that. So that's the average case of the order of n sorting. It's not going to be comparison-based approach. So if we have like this kind of inequalities, then the best we can do is the divide and conquer, and it's going to be end up being order of n log n. So the best performance of the comparison-based approach is order of n log n. So here we are not going to do this comparison. We are doing something smart here. We are going to use counting and numeric properties. And these are two variants of the order of n sorting. And the bad things here is the assumptions. Here we are making some assumptions of numeric property. Right? So that's one assumption added, so that's bad. However, it's the best time complexity that any sorting algorithm can achieve. Counting sorting works like this. So here the assumption is this. From the sequence contains integers ranging from 0 to k. This sequence always contains the integer. Being determined is going to be 0 to k, maximum k. So this is going to be maximum value of this sequence will not be greater than k, and minimum of this sequence is always smaller than 0, and it's going to be the integer values. Then what you can do is count the occurrence and produce a sequence based upon the count. So let's imagine that we have this property. Then what you can do is create a small array called count. And count is going to be here, index is going to be 0 to k. So it means that we can do to count 0 and to count k. And then what you want to do is that you are just going to do add the 1 for each occurrence of these integer numbers. So here, actually, let's assume that we have the 1 as the minimum value and 9 as the maximum values. So how the actual counting sort works is that count 1, we are preparing this array here, count 3, count 4, count 5, count 6, count 7, count 8, count 9. And then we have this one iteration, and then we count it. So we see 3 here. Then we add 1 count here, like this. And then we see 7 here, and we add 1 count here. We see 1, 8 here, we add 1 count here. We see 5 here, 1 add 1 count, 2 here, add 1 count, 1 here, add 1 count, 9 here, add 1 count. 5 here, add 1 count more, 4 here, add 1 count here. And after that, from here, from this count 1, we are going to output the index numbers as the count numbers. So we have one index number 1, and the count is 1, so we just output 1 and 1 time. We have index number 2 and just 1 time, so 2 here. We have index number 3 and just 1 time, 3 here. We have index number 4 and just 1 time, so 4 here. We have index number 5 and count 2, so 5, 5, 2 times. We have index 6 and count 0, so we have none printed out. We have index 7 and count 1, so 7 here. We have index 8 and count 1, so 8 here. We have index 9 and count 1, so 9 here. It's being sorted. All right, interesting, right? So it's being sorted out. The time complexity here is that you have to do the n iteration by the counting. In the printout phase, you have to do the k iterations. Here, the r is equal to k in these assumptions. So order of n plus r. N is often to be is going to be the dominant values, and R is going to be the range values. So sometimes R is bigger, or N is bigger. But the thing is that it's not the multiplication, so it's just a order of N plus order of R, right? If it is just addition, we can split it into two pieces. And then it's going to be anyhow 4 into order of n categories, right? Because that what you can do is multiplying C here anytime you want. That's the big O notation's characteristic, right? So surprisingly, we have order of n performance. And there is no comparison here. There is no inequalities here. If we see any of these inequalities in these routines, it's going to be poured into comparison-based sorting, and it's the best performance would be limited to order of n log n. Because we are not using the inequalities, we are achieving order of n time complexity. Actual implementation looks like this. So we have random number generation, preparing the counting space, right? And actual counting of the values, and then printing out the counted numbers. So from here to here is the actual, the substance part of the counting sorting.